All right. I wish I could be there with you today, but I'm glad we can do this way. And the nice thing is you'll now have these three theorems we're about to cover in a YouTube format, video format, so you can cover them over the weekend to kind of review this. We're going to look at theorems 21, 22, and 23. So be sure that you've got your textbooks open. I think that's 95, 96, 95, 96 will be your page numbers. Let's go ahead and look at section 219. Your homework is written on the board over there, wherever it is on the board. And so you can get that, and I'll check that on Friday, okay? Let's go ahead and look at theorem 21, and then we'll do 22, 23. 21, theorem 21 says that if the opposite sides of a quadrilateral are equal, so opposite sides, the top and the bottom, and the left and the right are equal to each other, then the figure is a parallelogram. Now remember, quadrilateral is just a four-sided figure. The parallelogram is what we want to go to, whereas it's a quadrilateral whose opposite sides are parallel. So the goal of this whole theorem is to show that equal sides is going to translate into parallel sides. All right. So how do we do that? We'll look at our figure. We have ABCD as our given quadrilateral. We have our opposite sides, the top and the bottom, AB to CD are equal. So we have them marked as equal. And we have the left and the right sides, AD and BC are marked as equal. And so we have them marked as such also. So how can we show this equality turns into parallel sides? So what would be the analysis down here? What my definition must be shown? What is going to be, does that mean in terms of our drawing? And then what process might we use to show that? So let's answer those questions. In terms of definition, we want to think about the definition of a quadrilateral. We mentioned a minute ago, a quadrilateral is a parallelogram is a quadrilateral whose all the opposite sides are parallel. Page 93 for that. So by definition, we need to show that the opposite sides of this quadrilateral are not merely equal, as in our given, but that they're parallel. That gives us a parallelogram. So how do we get from equal sides to parallel sides? That should get you thinking about the angles of these sides, which gets you thinking about triangles, right? So we want to show then, in terms of the drawing, that our opposite sides, top and bottom, are parallel, not just equal. Our left and right sides are parallel, not just equal. So let's do that again, thinking about triangles. If we were to make a triangle out of these, we'll talk about how we do this line in a minute. If we condense this into two triangles, then we can show these two triangles are congruent by SSS. Well, how do we know SSS? No other. Well, we'll have to work it out and see. But the way we probably want to do that is I already see that two of the sides of this triangle are going to be equal by given. It's easy to show this third. I don't want to use SAS or ASA because I don't know anything about the angles yet. Theoretically, you could, but this is just the easiest way. So if by SSS, I can show that both of these triangles are going to be congruent, then since I have corresponding parts, now I can show that the angles are going to be equal, which is going to let me show the alternate interior angles is going to let me show the lines are parallel, hence a parallelogram. Let's see that in action. So start always with our givens. ABCD is a parallelogram, and that the tops AB and CD are equal, and that the left and right are opposite sides, AD and CB are equal. So that's listed as a given, right? Number two, we want to make two triangles by drawing a line between A and C. Now, how can you draw a line between A and C? Well, that's just the definition of a straight line. 2 points determine a straight line. Easy enough. Those are those early examples that should be in your book, right? Next, we have, how do we know then that AC equals CA? Now pause. Why are we going to show AC equals CA? Remember, we want to try to show these two triangles are going to be equal, right? And so what we're going to show is that this is equal to this is equal to this, and this then has to be equal to this. That's where we're trying to show that AC equals CA. We'll see that strategy in the next line. But how do we know that AC equals CA? Well, it's because it's the same line. That is the law of identity. So AC equals CA, but now it's easy to show that the two triangles are congruent. Triangle ABC, the bottom, just is congruent to triangle CDA, the top, because of side SSS theorem, because we know that the left and the right side, AD and CB are going to be equal because of given. We know the tops and the bottoms, AB and CD are equal because it is given. And then this, we just shown that AC and CA are equal because of identity. So now we know these two triangles are themselves congruent, right? So we've gone a long way. We've so far gotten into showing that the two triangles inside of here must be congruent. This is going to give us then the fact that if you go by CPCTE, remember corresponding parts of congruent triangles are always going to be equal. So we know that M is going to be equal to S and N is going to be equal to R, because if you were to imagine taking this as a piece of paper and folding it over, then those are not folding over, I'm sorry, turning it over, so that you just take this whole thing, kind of turn it this way so that the angles all line up. Then M corresponds with S and R corresponds with N. They're going to be equal. And since they're equal, now we've come to, this is number 6 is really, we're going to prove our theorem, because we know now we can show that AB is actually parallel to DC, this opposite, and that, I'm sorry, AB, yes, is parallel to DC, and that AD is going to be parallel to BC. The bottom is parallel to the top and the left is parallel to the right. How do we show that? We're going to go to Theorem 7. If you need to, pause the video. Anybody pause? And when you're there, go look at Theorem 7. Go and pause it. Assuming you pause it and you're back, now you read this, that when two straight lines are cut by a transversal, and those transversals form alternate interior angles, those lines are parallel. So we have this straight line, AC, this straight line, DC. Well, look, they're cut by a transversal, AC. Well, we've just shown that N and R, they're alternate interior angles, and they're equal. We know that because the CPCTE above. Well, that means if the alternate interior angles are equal, then that means these lines themselves must be parallel. The same is true for our left and right sides. So left side and right side are straight lines. They're cut again by the transversal, where S and M are alternate interior angles. Since those are equal, then these also must be parallel lines. But now we've shown that the left sides are parallel to each other. The left and right are parallel to each other. The top and bottom are parallel to each other. That means that ABCD is not merely quadrilateral with equal sides. It's also a parallelogram because of the definition of a parallelogram. So to summarize then, Theorem 21, anytime you have a quadrilateral, which both of the opposite sides are of equal length, then you can also show, therefore, that the opposite sides are going to be parallel to each other, which just makes it a parallelogram. All right, so much for Theorem 21. Review that as you want as time permits. Let's go ahead and do Theorem 22. So here, rather than working with both sets of opposite sides, we're going to pick one set of opposite sides and say that if two sides of the quadrilateral are equal and parallel, so Theorem 21, we just had them as equal, but now we have one set of opposite sides that are equal, and we're also given that they're parallel. Then from here, we can go ahead and show that the figure is also a parallelogram. So again, here's our givens, where our top, we're the tops here. Top and bottom, A, B, and DC are not only equal, they're also parallel. The analysis, we're going to see exactly the same. So let's go ahead and take a look at this. Our givens, again, A, B, C, D is a quadrilateral, that A, B, and C, D are both equal, and we're also going to, they're parallel to each other. So let's go ahead and again, draw a line between points A and C. We know we can do that. That's 2 points from a straight line. Now I can say that angle BAC, which is unlabeled in your picture, and angle DCA, unlabeled in your picture, that these lines are going to be equal. How do we know? It's again theorem. Theorem 8, which is that if two parallel lines are cut by a transversal, then the alternate interior angles formed are going to be equal. So we have this angle. So now we know that they're parallel by given. We know this is a transversal. Therefore, this angle and this angle are going to be equal. Now I know again that AC and C are the same. Once again, by identity, perhaps you can see where this is going. I have now this triangle. This top triangle right here is going to be equal to the bottom rather than SSS, because I don't know anything about the sides, right? But now I've allowed to use this line is equal to the bottom line. The top is equal to the bottom. Then the angles, in this case, the unlabeled angle at the top, the unlabeled angle at the bottom, and then the are equal, and then the line through the diagonal is equal. That's side, angle, side. So SAS tells us the top and bottom triangles are again going to be congruent. Once again, CPCTE, I can now show that R and S are going to be equal because, again, that's the corresponding parts of the triangles. But you might, it's that now that this is equal, now I can show that AD is parallel to BC. Well, why? I have these two straight lines. The alternate interior angles, that's the thing we did before in the previous, are equal. Therefore, the lines must be parallel. Therefore, all four sides are parallel, which gives us a parallelogram. Not all four sides. The two opposite sides are parallel. So we were given the top and bottom opposites are parallel. Now we've proven that the left and right sides are parallel. Since all of them are parallel to each other, the left and right are parallel, top and bottom are parallel. Therefore, that's the definition of a parallelogram. So we've shown theorem 22. Once again, go back, review that until that kind of makes obvious sense. The strategy, again, was to show that these sides in here, these triangles, are congruent, which means the angles inside are congruent. And if the angles inside are congruent, if you think about the tops or the opposite sides as being transversed, then you can show those lines are parallel. Let's finish up on theorem 23. Now here we have, once again, a quadrilateral ABCD. And if we have both diagonals, if they're going to bisect each other, if the diagonals inside bisect each other, then you're always going to know that this is a parallelogram, or you can show that it's a parallelogram. So how are we going to do that? So we're going to take this given that ABCD is a quadrilateral. We have these diagonals, AC and BD. We have them intersecting here in the middle at O, such that they bisect, so that AO is equal to OC and BO is equal to OD. All right. So if we have these bisecting diagonals, how do we know the whole quadrilateral is a parallelogram? So the analysis is we're going to use theorem 22, which we just did, to show this makes a parallelogram, and we're going to show them in terms of the drawing. So let's answer those questions. By theorem 22, what must be shown to make ABCD a parallelogram? Well, by theorem 22, go back and look at it again. Theorem 22, we had to show that if two sides are equal and parallel, then the figure is a parallelogram. So once again, if two opposite sides are both equal and parallel, then it's a parallelogram. So in this sense, this would mean let's take either AB and DC and show they're both equal and parallel, or we could do it with AD and BC. So either the top and bottom have to be equal and parallel, or the left and the right have to be equal and parallel, whichever you want. Let's work this out then as we finish up. Start stating our givens in our proof as always. So ABCD is in fact a quadrilateral, that we have AC and BD that are going to bisect each other at point O, such that AO is equal to AC and such that BO is equal to OD. So again, all that is both stated and drawn here in your givens. Now, we now know that angle AOB, see this angle right here, is going to be equal to angle DOC or COD. How do that? That's just the definition of a vertical angle. You should have that again in your notes. Vertical angles. They cross each other. Therefore, these two angles are going to be equal. You can imagine we are going to be what we've chosen to work with these, the top and bottom opposites. We could have done the same thing with the left and right if we chose to work. And that way, we're going to choose to work with the top and bottom opposites. So now we can already show very, very quickly that triangle AOB is equal to, or congruent to rather, triangle COD. How do we know that? SAS. We were given that this side and this corresponding side are equal. We know by definition of a vertical angle, and then step number 2, that the angle is equal. And we know the third side, or the second side, the third side, the SAS is equal. So S is equal, A is equal, S is equal. Therefore, these top and bottom triangles are congruent. Now, if they're congruent, we can start identifying corresponding parts of congruent triangles being equal. In this case, we know that AB has to be equal to DC. Now, remember, we didn't have that before. All we had was the equality of the diagonals in the middle. Now we know the actual top and bottom are actually equal. We also know that angles COD DO up here are equal to angle ABO. So this angle is equal. Well, how do that? Again, corresponding parts of congruent triangles. But now one step to finish our proof. We know, therefore, that not only is AB equal to DC, because that's corresponding parts of congruent angle, we also know that they are parallel to each other also, because they are straight lines. They are cut by a transversal. Remember that this angle and this angle are equal to each other because of CPCTE. But if the angles are equal to each other and they make corresponding interior angles, imagining CD is a line, imagining AB is a line, transversed by AC, here's your corresponding interior angles. Since they form alternate interior angles, I'm trying to say rather, that makes those lines also parallel. That is theorem 7. So therefore, we've shown per the last theorem that theorem 22 again, that you have AB and CD are parallel, which means therefore they simply are a parallelogram. So having done that, you can review this video until this makes sense. I hope you have written them out, followed the steps, drawn them along as you've done. And if you do that, I think you'll pretty quickly see that the theorems ought to be pretty self-explanatory. So any questions, you have my email, reach out to me over the weekend. I'm always around. I'll see you on Monday. Make sure that you do the assignments. I'm not going to say on the video because I have forgotten what I wrote. I know it's exercise 219. If you have any questions, reach out, and y'all have a blessed day. Thanks so much. Bye.